Here we have only one variable. We can add to our mix another symptom, let's say. So we currently we have 20 people who are having flu and 50 people who are having cold, and then they are all sneezing. People who are not sneezing, they are about 30 and 50, right? Then we can add another variable. We can say, let's measure their temperature as well. Some people who have fever, some people who have no fever. So we measure that about 45 of people who have flu, they have fever, and about 5 of them, right? And so this is another dimension here. So we have 2 variables, sneeze, no sneeze, fever, no fever. We can answer the same question very easily. Probability that the person has cold, given that the person has this condition, sneezing and fever. So we will calculate it as, this is our posterior probability. We want to compare it with is it greater than the probability of flu, given that the person is sneezing and the person has fever, right? Whichever is greater, we will say, yeah, the person is in flu class or cold class. How do we calculate this? This is posterior, we calculate the likelihood. Given that the person has cold, what is the probability? Person will be sneezing, multiplied by probability of fever, given that the person has cold, multiplied by probability of cold. So 2 conditional probabilities multiplied by cold, divided by probability of sneezing and probability of fever. Now this is going to be the same denominator for this equation. For this number, we have to calculate probability of sneezing, given that the person has flu, multiplied by probability of fever, given that person has flu, multiplied by the prior probability of flu. Whichever is greater number, we will classify the new person, the test person, in that class. Now, here is the deal. We can only calculate the conditional probability of having a disease, a diagnosis, given 2 symptoms or more symptoms, as simple multiplication of their conditional probabilities. Only in one case, we assume that these conditional probabilities or likelihood of, let's say, A and B, right? Or instead of A, we give them proper names. Sneezing and fever, they are independent. That means if person is sneezing, there is no way we can say that the person will have fever. So the probability of sneezing given fever is equal to probability of sneezing. They are independent. And vice versa. If we know the person has fever, we cannot say anything that the person will be having sneezing condition. But in reality, we often see that this kind of independence assumption is not real. In fact, these assumed independent variables are dependent. When somebody has fever, they often sneeze. When somebody is sneezing, they often have fever. But due to this assumption, we can calculate our posterior probability as multiplication of simple conditional probabilities, likelihoods. Due to have this facility to be able to apply naive Bayesian formula, we make this assumption, which is naive assumption. We intentionally become naive, right? And due to this assumption, we call our naive Bayesian classifier as naive Bayesian classifier. not Bayesian, naive Bayes classification or classifier, right? So this is, even though naive assumption, we want to ignore the interactions between independent variables, but it is very powerful assumption. Due to this, we can calculate and classify new data points, new people very easily based on only this contingency table. If there are 2 variables or 20 or 200, we will just maintain a table of counts like this. And we will calculate the marginal probabilities, right? And we will calculate easily the joint probabilities, which is dividing by the total, right? So these marginals will help us figure out this part of the formula, and joint will help us figure out this part of the formula, and joint by marginal is conditional. The conditional is our question, right? Our classification question. What is the probability given that person has this symptom? What's the probability person has cold? We will compare it with probability of flu given the same symptoms. Whichever probability is higher, we will classify the person or the object or the data point to that class. And this is how this solution we have here is referred to as a turnkey solution. We don't need to work too hard to maintain these counts. It is a naive assumption, but it enables powerful solutions which we can use to at least get the minimum possible accuracy or precision and recall on classification problems. And you can easily figure that out based on this table. Create naive Bayes solution to find out the minimum possible accuracy that you can get. And naive Bayes is just 3 probabilities playing together: joint, conditional, and marginal.